Hello students, today I will be starting with the other topic, a new topic, and as you can see, it is modern physics unit 3 for for our engineering physics course for BTech. All right. So the topic which I will be discussing is Compton effect. This is the topic. This topic I will be discussing. Compton effect I will be discussing for unit 3. All right. First, I will give you the definition of Compton effect. The definition says when a monochromatic beam of high frequency radiation is scattered by a substance, the scattered radiation contains two types of wavelengths, one having same wavelength as that of the incident radiation, while the other having the wavelength which is greater than that of the incident radiation. So this effect is known as the Compton effect, and it was first observed, as you can see, it is written, it was first observed by A.H. Compton. All right. So this effect he has observed, and then he found that why these things are happening. It means that why when a monochromatic beam is falling and it is scattered, so why we are getting two scattered beams, and that also of different wavelength. So he gave explanation for this effect, and he used some quantum mechanical concepts for the explanation of this effect. All right. Let us see how he explained. He basically used some assumptions. These assumptions are that he said that Compton effect is the result of interaction of an individual particle and a free electron of target. Target means the material on which the monochromatic beam is allowed to fall. So he's saying basically he has used the concept that when the beam is falling on the target, so the beam or the photon which is present in the beam, that is interacting with the electron which is present in the target, and it is the free electron which he has used. All right, the free electron is interacting with the individual particle. Here individual particle is the photon of the incident beam. Then the next point, the next assumption which he has used is that the collision between this photon of the incident beam and the electron of the target material, that collision is relativistic and elastic. Then the third assumption, he has said that the laws of conservation of energy and the momentum, they hold good in this interaction. So these are the assumptions on the basis of which he has explained the Compton effect. All right, the theoretically he has explained. Again, we can see in this diagram, it is mentioned what activity is actually taking place when the beam is incident on the target material. Here you can see that the beam is incident on the target material. This is the target material, and this here it is, the beam is shown in terms of the incident photon. So the photon of energy h nu is incident, and here where the target material is present, we are having the electron which is present in the target material. All right, this part. So electron is present here. Now the beam will fall on this electron, and the interaction is going to take place as has been told by Compton. And as a result of the interaction, let us see what is going to happen. We can see in one of the direction, we can see that the electron starts moving, and in the other direction, we can see that we are having a scattered photon. So this is what is happening. Actually, what is now happening, we must understand that the incident photon and electron, they are interacting, and a certain type of energy transfer is taking place between this photon and the electron. So what happens when the electron, which is initially at rest, it gets energy from this photon, so it starts moving. And this is the way, this is the behavior of the electron when it is moving. All right. So the electron is moving in one particular direction. So one of the scattered beam we are getting in this direction. So one of the reason for scattering is this. Now what happens? The remaining energy which is left here as a result of the interaction, which is not used up till yet by electron, that remaining energy is scattered in the form of scattered photon. All right. Now, so in this way, this is how when the incident photon is falling on the target material, this is how we are getting two scattered beam, which was mentioned in the definition of the Compton effect. So these are those scattered beams. Now the problem is, or the discussion can be that why these scattered beams are different in wavelength. Again, if we concentrate on the interaction, we can see that the electron which has obtained energy from the photon, so the electron starts moving with that energy. So that means one scattered beam is obtained with this type of energy. All right. Now the other scattered beam, how it has occurred? It has occurred because the remaining energy which was there. So with that remaining energy, that beam, second beam has scattered. So it's very natural when the second beam has scattered with the remaining energy. So then it will not have the same energy. So it will not have the same wavelength or frequency. And also not only this, it will have a lesser energy as compared to the energy which the electron is having. So since the behavior of this electron is different, it is a recoil electron, isn't it? So recoil electron is having the energy, and this scattered photon is having a lesser energy because it is using only the remaining energy. So when it is having a lesser energy, so if we look at the expression or relation of energy with the photon here, this part, all right, this part. If we look at this energy, all right, this h nu, all right, all of us know that E, which is the energy for the photon, is equal to h nu. This is the relation between the energy of the photon and the frequency nu. So if energy is less for this scattered photon, all right, so therefore the frequency of the scattered photon will also be less because h is constant, Planck's constant. So what will happen? And once the frequency nu dash is less, so the frequency and the wavelength, they are inversely related. So if for a particular photon the frequency is less, so then the wavelength for that wave which is coming here, so that will be larger. So this is the reason why the other scattered beam which is obtained in Compton effect, it is having a larger wavelength. So this is the reason. So with this diagram, we can clearly understand what exactly is happening and why the Compton effect is taking place. All right. Now what happens? We can use, once we understand the effect, that how all the things are happening, we can measure certain parameters. Like we can measure how much difference is there between the two wavelengths which are scattered. All right. One we already know is equal to the incident wavelength, but the other is different. And we know that the other is having a larger wavelength. So we can, by studying these concepts, by using the parameters, the relations, the interactions, we can calculate that how much difference is there, and can we minimize the difference, or if the difference between the two wavelengths is larger, then it is beneficial, or it is giving a good study, or it should be minimum, things like that we can do. So that is what was done by Compton. All right. So, and he has used certain assumptions in doing this. Like, as you have seen that he has used certain assumptions, That means now, and these assumptions we have already discussed. The first one we have discussed, that the Compton effect is the result of interaction of an individual particle and free electron, that we have shown how this was there, this part, all right. And then we have, we come to the second assumption, the collision is relativistic and elastic. This is also, we have studied here. Now, and the third assumption was what? The third assumption was that the laws of conservation of energy and momentum, they hold good. So, we can make use of these laws, conservation laws, that is energy conservation and momentum conservation. So, if we look at this part now, so it is using the energy conservation law, and the law says that the energy before the collision must be equal to the energy after collision. So, that is why the energy before collision and the energy after collision, it has been calculated. We can see that the energy before collision comes out to be h nu plus m naught c square. So, how is it written? We can look at this. Before collision, we are here. All right. So, before collision, this incident photon is having energy, and it is having energy, let us say h nu. And before collision, what is happening to this electron which is present in the target material? The electron is at rest because there is no collision. So, it is at rest. All right. So, what happens at rest? If we use the concept of relativity, so the at rest, we are having the rest mass m naught. So, that is why the energy, this rest, the electron which is at rest, that electron is having the energy m naught c square, which is the rest mass energy or simply the rest energy. All right. So, now then we come to the energy which is which can be there after collision. So, let us see what can be the energy after collision, what will happen after collision. Again, we refer to this diagram. After collision, what will happen? After collision, we can see we are getting two scattered beams. All right. One of the scattered beam is due to this recoil electron, and the other scattered beam is from the scattered photon. So, the recoil electron must have a certain type of energy which is related to the mass. Earlier, when it was at rest, it had the energy, rest energy, m naught c square. Now, it is in motion. So, its mass changes from m naught to m simply, and the energy becomes mc square. And the next energy which we will have after collision will come from the scattered photon, that will be h nu dash. So, this way the energy after collision can be written as h nu dash plus mc square. Then we apply the conservation of energy principle or the law, and we write down h nu plus m naught c square, which is before the energy before collision, equals to the energy after collision. So, this expression is obtained. And if we further simplify it, so then we can have the equation 1 now. mc square is equals to h nu minus h nu dash plus m naught c square. We can have it like this. So, this much study we can get if we apply the conservation of energy to this activity of Compton effect. All right. So, this much study we can get. Now, the next study we can obtain by using the conservation of linear momentum. If we apply the principle of conservation of linear momentum, so we can obtain this much study, the other part of the study. All right. So, how do we do that? Since the momentum is a vector part, it has a vector type of behavior. All right. So, we have to take care of the components, the direction here. Like x-axis, we can calculate separately the momentum along the x-axis, we can calculate separately along the y-axis. So, we start with the x-axis, all right. So, the momentum conservation law is the momentum before collision again, and is equal to the momentum after collision, should be equal to the momentum after collision. So, this should be the law, and we apply the law only along the x-axis initially. So how we will apply it? Let us see. Again, we can take the help of the diagram. All right, here. So if we look at the momentum before collision, so it is P is equals to h nu by c. This is the momentum for the incident photon, because up till now collision has not occurred. And we know that when the collision is not occurred, so this target electron is at rest. So this is h nu by c, and then this electron is at rest. So there is no momentum. So the momentum becomes 0. So then this is the part. H nu by c plus 0 is here. All right. Now we go to for the momentum which is after collision. After collision, what happens? We are having two scattered beams. So after collision, we are having momentum for this recoil electron, and then we are having momentum for the scattered photon. All right. So, and what is this? For the recoil electron, we are having mv, and for the scattered photon, we are having h nu dash by c. So we'll write down this momentum here, which is this, along with their components. All right, h nu dash by c cos phi, because so that it becomes in the x direction. Similarly, mv cos theta, so that it comes in the x direction. So now in the x direction, we are having this momentum conservation, and again we can rewrite. So we will have mv cos theta is equals to h nu minus h nu dash cos phi. So this will be our equation 2. We will now go for the momentum conservation in the along the y axis. If we do this, so we have to write down first the momentum before collision in the y direction. All right. So what we will do, we will look for the y direction. Here you can see that the incident photon is incident in the x direction. So if we look for the y component, so we will not find any y component here. So for this reason, we are having 0 here. All right, before collision. Now we go for the momentum after collision in the y direction. We will definitely find, because we can have this p sine theta and then again p dash sine phi. So that those parts will give us the momentum along the y direction. So this will be 0 is equals to h nu dash by c sine phi for the photon, and minus mv sine theta. So this minus sign is helping for the error which can come due to the direction. All right. So to bring all the components in the same direction, the minus sign has come here in place of plus. Again, we rewrite this expression and we obtain equation 3. mv c sine theta is equals to h nu dash sine phi. Okay. All right. So now next, these are the calculation parts. You must remember that we are using the effect to calculate the changes in the two wavelengths. Afterwards, we will give the name of that part. All right. So first we will see what we have done. We have squared this equation 2 and 3 and then added, so that we are able to obtain this equation 4. All right. After squaring equation 2 and 3, we are able to write down equation 4, which is m square v square c square is equals to h nu square plus h nu dash square minus 2 h nu dash cos phi. So this part we have done. All right. Now, and these parts we have used from the momentum law. All right. Now we can use this energy law and we can obtain certain expression again, which will help us to obtain the relations between the scattered wavelengths. So what do we do? How do we use the energy part? We simply square equation 1. This was our equation 1, this one, which we have obtained from the energy. So we simply square this equation, and when we square, so we are getting m square c to the power 4 m naught square c to the power 4, and this long expression. And this expression we have given the name equation 5. All right, now the next step of calculation which we are doing is we are subtracting equation 4, this one, that is from equation 5, this one, and we are getting equation 6. All right. So starting from this step, all right, we are doing certain calculations or simplifications to obtain the relation between those scattered wavelengths. All right. And again, in this calculation, we are using certain relativistic concepts also. As you can see earlier only that we have used m naught itself. So m naught itself is a relativistic mass, a rest mass, all right. So we are using the concept of relativity where m and m naught are related. All right. So now we use this formula m square c square minus m square v square is equals to m naught square c square. All right, and we multiply this expression on both the sides by c square. So what do we get? M square c to the power 4 minus m square v square c square is equals to m naught square c to the power 4. This we have given the name equation 7. But what happens when we obtain this? We can see very carefully that we have obtained somewhat this part here also. You can see this expression. So that is why we were doing all those calculations. So we are able to obtain this same expression by equation 7. So which means that we can eliminate that expression by using equation 7. All right, we can eliminate this expression which was obtained in equation 6. So that because it is having various other terms, it is having velocity, it is having mass, it is having the c, velocity of light also, and it is not having any term for the wavelength or the frequency. So it will only add to our calculations, it will only make it complex and it will not give any result for what we are working. So we can eliminate. That is why we have done this part. So when we eliminate, you can see here, if we eliminate, so we are getting 0 is equals to 2 h nu dash cos phi minus 1 plus 2 m naught c square h nu minus h nu dash. All right. Again, we rewrite. We are having h nu dash and h nu here also. We are having h nu and minus h nu dash here. So we can bring all the frequency terms on one side, which is this, like this we can do. When we bring all the frequency terms on one side, it will be like this. So nu minus nu dash upon nu dash. All right. So this is h by m naught c square and 1 minus cos phi. You can see now we have obtained much valuable result. A result which we can at least relate, because here it is frequency and it will not take us much time to convert this result into wavelength. That was our aim. We wanted to study the difference between the wavelength, the relation between the scattered wavelengths. All right, the exact relation. So once we have obtained the expression for frequency, you can see here by equation 8, this is 1 by nu dash minus 1 by nu is equals to h upon m naught c square 1 minus cos phi. So this is the expression for the frequency. Now, as I said, it will not take us much time because this is the relation between the frequency and the wavelength. All right. So we will obtain the same expression in the terms of wavelength. As you can see, we have done what we have done. We have obtained the expression in terms of the wavelength. All right. So this is lambda dash minus lambda and h upon m naught c 1 minus cos phi. Alright, so delta lambda is here. So this is delta lambda, lambda dash minus lambda and this. So this is the difference between the wavelength. You can see this can be the wavelength of the incident beam and this can be the wavelength of the scattered one. So lambda dash minus lambda will be the difference, and it has been given another name also, another specification also, that is delta lambda. So this is shift. This is the shift of the wavelength. All right. This is called as shift. And since Compton has studied these things, so it is Compton shift. So Compton shift is delta lambda, and how much is it? It is h upon m naught c 1 minus cos phi. So this is our equation 9, and this is how we can study that how much shifting has been taking place. All right. And this is a big calculation which Compton has given us so that we can identify the scattering, how the scattering is taking place, what type of scattering is having, and what type of shifting is taking place, and what are the factors on which the shifting is going to depend, so we can control. So what are the factors? So the factors are that the wavelength of the scattered beam lambda dash is greater than the wavelength of the incident beam. We have seen this in the result also. Compton has observed it in the experimental result, and now by the calculation of Compton shift, he has proved also. Secondly, delta lambda is independent of the incident wavelength. This part he has done. Then delta lambda, it is independent of the incident wavelength because you can see that it is h upon m naught c 1 minus cos phi. There is no term of the wavelength here. So that is why it is saying that it is independent of the incident wavelength. Delta lambda have the same value. Delta lambda has the same value for all the substance containing free electron. This is a big result which we can obtain from here, because it is saying that delta lambda, that is Compton shift, will be same for all the substances where free electrons are present. How it is saying this result? It is saying because h, you can see delta lambda is depending on h. So h is the Planck's constant. It is constant. It will have the same value for all. M naught is what? It is the rest mass of the free electrons. So if the free electrons are present in a material, so it will have the same value. C is the velocity of light, and phi. Phi is the angle of scattering. So if the angle of scattering is same, so then this delta lambda will be same. If the angle of it will not, like if the angle of scattering is same, it will not be different if I change the material, because the parameters of the material are not present here. So it will not be different for the material. That is what this result is saying. Then it is saying that delta lambda only depends on the scattering angle, which we have discussed just now, that it will only depend on that. Okay. All right. So some of the standard calculations or result which we can see for ourselves, and we can have knowledge also, that is we can give different values to the scattering angle phi, and we can obtain shift. So if the angle is phi 0, so then cos phi will be 1. So then delta lambda is equal to 0. So lambda dash will be equal to lambda, and that will give us the result. The scattered wavelength is same as that of the incident wavelength in the direction of incidence. Phi is equals to 90, so cos phi is 0. Delta lambda is h upon m naught c 1 minus cos phi, and if we substitute phi equal to 90, so this will be simply h upon m naught c, because phi goes off because cos phi becomes 0. All right, so phi term goes off. So delta lambda is, if we calculate all the values, because they are standard values, we can do it. The value of H is known to us, value of M naught is known to us, value of C is known to us, so we can do it. So this is 0.02426 angstrom, and since it is a standard value, it is a specific value, so certain name is given to this value, that is lambda C, and it is called as Compton wavelength of the electron. This is lambda C, this value. So Compton wavelength of the electron is given by this value. Again, when phi is equals to 180 degrees, if we put this, so cos phi is equal to -1. So delta phi is equal, delta lambda will be equal to -1 we put here. So minus and minus plus, so it becomes 2. So it becomes 2h upon m naught c is equals to 0.04952 angstrom. All right. So this is the value for phi equal to 180. Now this interesting question is there, that why the Compton effect is not observed in visible spectrum. So the reason depends on the wavelength only, because we can see that here. We can see that for the maximum value of the angle phi equal to 180, we can see that the delta lambda is 0.04952. All right. So this is the maximum shift which it can read, it can give. So the maximum shift which it can give or read is this much. All right. And the visible region, in the visible region, the maximum wavelength which we can have is what? The visible region is about 500 angstrom nearly. So that is why this effect is not visible in that region, because of the difference of wavelength. The maximum it can calculate only nearly 0.05, whereas the wavelength region for visible is 500 angstrom. So the percentage is not such that it can detect Compton effect or Compton shift. So that is the reason. All right. Some numericals which we can exercise, we can study, so that we can know how the Compton shift is taking place, how it is observed. So in the example, in the numerical, it is saying that show that the de Broglie wavelength of the particle is equal to its Compton effect, Compton wavelength, when its velocity is 0.707 c, where c is the velocity of light. That is all right. So I think it is clear. The question is very clear. The de Broglie wavelength of the particle is equal to the Compton wavelength. So de Broglie wavelength is having the expression lambda is equals to h upon mv. All right. And m is equals to, it is related to the rest mass as m naught 1 minus v square by c square square root. So we will substitute the value of v here, so that we have the value of m. So m is now obtained when we calculate the value. So m is obtained as m naught upon 0.707. Now we put this value of m in the expression of the de Broglie wavelength. So it is obtained as lambda is equals to h upon m naught c, and this is the same part which we obtain in the Compton wavelength. Here we have seen here this one. This is the Compton wavelength, lambda c. So it is obtained like this. All right. So now what happens? This is the part which was asked. We were asked to show that this de Broglie wavelength is equal to the Compton wavelength. So this we have shown. All right. And here in the next part, we can also show that what exactly is the numerical value of lambda c, that is the Compton wavelength. We can put h, like I told you, standard values. We can put with the value of m naught. The rest mass of electron, it is again standard, it cannot change if the electron is not changing. And c is the velocity of light. Again, the velocity of light is a universal constant. All right. Then again, we can have a different type of numerical here. X-rays of wavelength 1 angstrom are scattered from carbon block. We have to find various parameters here, like we have to find the wavelength of the scattered beam in a direction making 90 degrees with the incident beam. So we can directly use, for the first part, we can directly use the Compton shift expression, that is delta lambda is lambda dash minus lambda and is equals to h upon m naught c 1 minus cos phi or theta here. So we can put the value of phi 90 degrees here and we can obtain this expression for the delta lambda. All right. And from that expression, we will find out lambda dash, because the value of lambda is given as 1. So lambda dash is calculated like this, 1.0243 angstrom. All right. Then the next part, we have to calculate the kinetic energy imparted to the electron. So the kinetic energy which the electron is getting is equal to the difference between the energy of the incident photon and the energy of the scattered photon. That is h nu minus h nu dash. So the results are given in terms of lambda, that is the wavelength. So we will write down this expression in terms of wavelength, hc by lambda minus hc by lambda dash. And we will substitute for these parameters h, c and lambda dash and lambda. We substitute, so kinetic energy becomes like this. In terms of numerical, it is 4.72 into 10 to the power of minus 17 joules, and when we convert into electron volts by dividing with 1.6 into 10 to the power of minus 19, so it becomes 295 electron volts. All right, so then next part, what we have to calculate is the direction of the recoil electron. That is given by phi. Direction of the recoil electron is phi. So tan phi is lambda sine theta upon lambda dash minus lambda cos theta. And we will substitute the values of theta and lambda dash here. And you can see we can obtain by calculation the value of phi. Phi is equals to 44.4 degrees. All right. That is all which we had to discuss here regarding the numericals also. All right. These were some numericals. You can solve the same type of numericals and make your concept of the this Compton effect more clear. And apart from the book, all right, by S.L. Gupta, Dr. S.K. Gupta, we have referred to the internet also. So you can also go on and check for these concepts and find out what they actually tell you and how they what are the applications for this effect. All right, we will talk about another topic on the next lecture. All right, thank you.